I'm Jakob Tum. I'm a PhD student at the Technical University of Munich, and today I will show you how future generations of robots can safely work together with humans. Together with my co-author Matthias Althoff, we developed a safety shield for reinforcement learning-based manipulation that ensures human safety without critically reducing the robot's freedom of movement. In the past few years, researchers demonstrated the enormous potential of reinforcement learning in complex manipulation tasks. The task complexity thereby increased from simple pick-and-place task to multi-object and even multi-objective manipulation. Unfortunately, this vast potential cannot be exploited when working next to humans, since we cannot guarantee that all actions outputted by a reinforcement learning agent are safe. Naturally, errors or misbehavior are completely unacceptable when operating a robot next to humans. We therefore want to ensure human safety. One way of doing that is to guarantee that the robot is at a complete stop before any human could reach it. This is a form of speed and separation monitoring. We can therefore define our problem as follows. We want to control a manipulator in a human environment. We have to guarantee that the robot is at a complete stop before any human could reach it. And the goal is to move the manipulator from an initial position to a randomized goal joint position while evading the human in the scene. In traditional reinforcement learning, the agent outputs an action to the environment, which in our case is the manipulator. After performing the action, the environment sends its current state and a reward back to the agent, and the loop repeats. In this setting, we of course cannot guarantee that every action executed by the environment is always safe. More so, since the agent wants to explore the state space to find its best policy, it is very likely that at some point it will pick an unsafe action. We therefore propose to add a safety shield to the agent's action output. And that safety shield should only output safe actions to the environment. Our safety shield checks the safety of actions during their execution at a high frequency and only intervenes if it's strictly necessary. In essence, our safety shield consists of three core components: a long-term planner, a fail-safe planner, and a verification. The long-term planner translates the agent's action to an intended trajectory that the robot should follow if there's no danger of collision. The fail-safe planner plans a trajectory that stops the robot as fast as possible. Our verification is based on a reachability analysis to capture all possible human motion. At each time step, we calculate the entire set of states that the human could occupy and the time that we need to stop the robot. Then we check if we could execute one time step of the intended trajectory and would subsequently still be able to bring the robot to a complete stop using the fail-safe trajectory without colliding with the human reachable set. If this check would fail, we could still execute the previous fail-safe trajectory. We can therefore guarantee that the robot is at rest before any human could reach it. Our experimental results show that only our safe agent using our safety shield is able to reach the goal consistently without colliding with the human. The baseline agent, however, did not learn to avoid collisions effectively. The benefits of our safety shield are even more clear when the human blocks the fastest path from the start to the goal position. In this case, the baseline agent did not learn to move to the goal at all. Using our safety shield, the safe agent learned to evade the human effectively and reach the goal consistently. For those who are interested, our safety shield and the training environment are available on our GitHub, and I look forward to the opportunity to discuss this paper further with you in the upcoming Q&A session.